This lecture is going to begin our lab exercise involving astronomy, and particularly our solar system. So we'll be looking at the formation and evolution of our solar system itself. We're going to be using the term Nebular Hypothesis, and it's simply stating that this debris field of gas and dust and ice and rock and all these fragments of particles that are quite disorganized begin to organize themselves sometime about 4.6 billion years ago. And the sun accumulates, right? Gravity takes over, and it starts begin pulling in this to the central location. And the sun consumes about 99.85% of all this matter. And you'll see that it continues to contract and contract. But in the outer debris field, this region in space that you see these individual lines, well, they start gravitationally accreting and building their own planets. And so really our planet comes from this nebular hypothesis, and the objects that are orbiting here simply follow the rules of physics. And we'll be using the term conservation of angular momentum to make sense as to how and why the planets formed and why they're orbiting the Earth in this counterclockwise manner. And so here we go with the planets themselves, and we can look at it in this picture, or we can look at it in this picture. But Mercury, Venus, Earth, Mars, we've got this asteroid belt here between Jupiter, Saturn, Uranus, and Neptune. And notice Pluto doesn't make the list, and we'll talk about why that is in a little while. But I do want to make sure we emphasize that the rocky interior planets are located or situated extremely close relative to the size of our solar system. And notice outside of Neptune, we could even find the location of where Pluto would be. And then look even out here further, we could talk about the Kuiper Belt. And even out further, we would talk about the Oort cloud. So we'll be adding some layers onto, it's not just our solar system, but we'll start off with our solar system. Notice this is a side profile of our side view of the solar system. In this case here, we've had the sun, centralized, central location, and that this disk shape is a structure that reflects conservation of angular momentum. So here I've got this nebular hypothesis, this cloud of gas and dust, 75% hydrogen, 24% helium. This became unstable, and the densest part began to collapse, and gravity pulled the material in toward the center, and then the disk shape formed. And the disk shape is simply a reflection of how gravity interacts and creates these spherical objects that we call planets. Remember, spheres are geometric shapes that are three-dimensional, right? It's not a circle, it's a sphere. It's got a depth dimension to it. And it's really astronomy's kind of preferred shape. It's the easiest way to get a lot of packaged materials into one geographic area. So the sphere itself becomes the preferred shape of the cosmos because gravity is doing the packaging. So here's how nebular hypothesis, it kind of agrees, it shows us that the angular momentum is always conserved. And when we start pulling these materials together and it gravitationally begins to compress from this debris field here, if I look at this debris field in this picture, as the material begins to gravitationally pull itself together, we start getting a rotation. In this case here, the gravitational force attempting to collapse this cloud, well, once it begins to collapse, the cloud spins more rapidly as it collapses because of conservation of angular momentum. And in class we do a lab where we have a student sitting on a stool and they have weights in their arms, and we spin them, and then as they pull the mass inward toward the central rotational axis, they rotate much faster. And this is called the figure skater analogy, that when a figure skater pulls his or her arms in, he or she spins faster. As material in the solar nebula collapsed, this very idea plays out, and the general spin of our solar system takes place. It then picks up. And this leads to the general motions we observe, and that would be the counterclockwise motion. In this case here, this would be once again a cross section. This is the proto-sun, right, the primitive sun itself, and these would be proto-planets, the planets in their juvenile stage. They are forming. And as the nebula collapses further, the local regions begin to contract gravitationally on their own because of the instabilities in the collapsing, rotating cloud. The planets build themselves from the leftovers, the debris field leftovers, or the remains that didn't make it into building the sun. So this is where accretion theory and differentiation take place. So gravity's influence on a proto-planet. Differentiation means to separate. So we've got this cluster of a bunch of different debris and material. Well, notice after differentiation takes place, right, this differentiated body here, the densest material, typically the iron-bearing minerals, find themselves sinking into the core. Remember, the earliest phases of the Earth, it was a molten state. Therefore, it was igneous and liquid. So dense materials, just as we would put a rock, right, non-pumice, into water, it would sink. So the densest material sinks in the early molten stage of planetary development. Iron and nickel are found at the central core of the Earth. The lighter materials float. We find the lightest materials on the Earth outside the crust, right? This is our atmosphere. These are the gases that compose, these are the lightest materials. The Earth's crust, right? So the Earth's crust would actually be the least dense rock, and it's true. The Earth is one large-scale density column, with crustal rock the least dense of all layers of the Earth. And each of the layers have varying compositions and densities, and they increase as one travels towards the center of the Earth. So in general, the more iron you find, or the iron minerals, right, the more mafic the rock, the denser the layer. So we'll get into the sun and nuclear reactions a little further, but I do want to make sure that we understand, we begin dabbling on what it means to say E equals mc squared, that really we're talking about energy. Sunlight energy, pure radiant energy, is actually a result of matter being converted, that the photons that take about 8.3 minutes to travel from the sun to the Earth, it was, well, let's just say it's got quite its own storyline. We'll unravel that mystery. But it's matter converted into pure energy, and this is what we see as sunlight. And we can do some simple math here, and we can just simply say that if I take 4 hydrogen atoms and I fuse them together within the proton-proton chain in the core of a star, that the math shows me that it doesn't add up. And the reason is because if the atomic mass of hydrogen is 1.008 and I have 4 of them, I get 4.032. But helium has an atomic mass of 4.003, and that does not equal 4.032, right? 4 hydrogen atoms, and the missing mass is the conversion of that matter into energy. So we will be doing a lot of different scale modeling. We'll do a couple different examples in class. We'll do some on paper. We'll talk about the scale models of the hallway, and we'll be doing lab exercise calculations as well. So here's what we're going to be learning in this unit. We'll be talking about all the different objects, the celestial objects: Mercury, Venus, Earth, our moon, Mars, Jupiter, Saturn, Uranus, Neptune. I would even put Pluto in there. And we'll study the distances to and from the sun, the temperature of night and day, the number of moons, the number of rings, the densities, compositions, revolutional period and direction, rotational period and direction, and the path of the orbit around the sun. Here we'll be separating or differentiating the planets themselves. We have our terrestrial, inner rocky planets, Mercury, Venus, Earth, Mars, and we have our Jovian, or our gas giants, Jupiter, Saturn, Uranus, and Neptune. And each one of them has its own literal personality almost. And we'll be doing a lot with the scales, so make sure we get used to this. Mercury, Venus, Earth, Mars. We have our asteroid belt, very significant. We'll talk about that in a couple different ways. We'll talk about how the asteroid belt was the planet that never became a planet. Jupiter's gravity just didn't allow it to. And secondly, the asteroid belt has significance because these are potential collisions that could take place that could redirect an asteroid and, let's just say, collide with Earth like it did about 65 million years ago, that redirected the evolutionary path that, let's just say, paved the way for mammals. Then we move on to Jupiter, Saturn, Uranus, Neptune, and once again we've got this dwarf planet Pluto into the Kuiper Belt and even beyond. So here's a data table that we'll be looking at pretty frequently in class in this unit. And we'll talk rotation versus revolution, right? A rotation implies it's moving around an internal axis. A revolution implies it's moving around something externally. So rotation leads to day and night of Earth. The revolution leads to the calendar year. So the final statement here of this lecture is why isn't Pluto a planet anymore? Well, the IAU, the International Astronomical Union, said, well, there are rules to be a planet. One, it has to orbit the sun, which Pluto does. It must have sufficient mass to assume a nearly round shape. Well, Pluto does. But number 3 is where the caveat comes in. It must have cleared its neighborhood, which is another way of saying it must be the largest body in its orbital sweep. And you'll see that it actually crosses in to Neptune's orbital path, And as a result of that, rule number 3 says, you know what, Pluto can no longer be considered a planet because Neptune is larger than Pluto. Therefore, Neptune is the largest object in its orbital path or its orbital sweep. Therefore, Neptune gets the title as the planet, and Pluto is then considered a dwarf planet. And that concludes your first lecture on astronomy.